Thank you. Thank you. Thanks for this opportunity. I'm excited to be here. Hopefully you can hear me clearly, easily. Okay. Yeah, I'm going to tell you a little about the works that we are doing, and then I think with that you get a feeling of where this is headed to, and the evaluation of where this is going to cure cancer and all that. I leave that to you so you can figure out yourself. This is the biggest picture we took before COVID. I think the current size of the team is about 3 times this many people you see here. And what we're doing here is celebrating an experiment which we landed in October 2019. And by then we claimed that we outperform a classical computer. So the first experiment I'm about to explain to you is that experiment. So it has the word quantum in it somewhere. There you go. And it's highly cited. So you should know about it. Well, the whole thing rests on a superconducting chip, which we fab in the lab. And the idea of how to make these quantum processor goes back to 1960s. Well, at least the building block of it was discovered or figured out in 1960s or 1970s, which is a Josephson junction. So if you have 2 superconducting islands next to each other, the Ginsburg-Landau phase difference would set up a current between them. If the phase is different, then you get the current going between them. This phase is the difference between the phase of the Ginsburg-Landau or the parameters. And this is how you make it in the lab. You put a layer of aluminum down, and then you oxidize it. That's this barrier between them. That's an insulator barrier between them. And then you put another aluminum on top. And then this would essentially make a nonlinear resonance. And nonlinearity is very important here because it makes you an atom which you can have level spacing non-uniform like an atom, and you can address the levels individually. Usually we play with the two lowest level of it, and we call them a qubit. So it's a bit confusing language. The object is called qubit, although it has many levels, and the computer science called the 2 levels of a qubit. So we managed to confuse a couple of different ways. So in the lab, it looks like this. Let me see. In fact, you know what? I can even give you the qubit. So with that and a microwave, you can do this at home. So what I'm about to pass you around, and you have to pass it. You can take a picture of it, but you can pass it back to me. First, let me make it clear. This is made by a grad student a few years ago, so it doesn't belong to Google, so I can share it with you. What you're seeing in here is a 9 qubit, similar to what you're seeing in the screen. And this is the zoom-in view of this. So you would see this, and someone left a fingerprint on there. That's very strange. You don't need to touch it. But now you have to angle it a little so you see what is on the screen because of the thing. So what we're seeing here is a pattern of, maybe you start passing it around. So remember, everyone have about a minute, right? You see a capacitor. Well, what are you seeing is a silicon, which is there's a 200 nanometer of aluminum on it, and then you do a lithography pattern on it. But in every color you see is the Photoshop color. There's no color in there for the end. So this is a capacitor of the junction I mentioned of the qubit of the nonlinear resonator. And there is Josephson junction I was mentioning is a tiny object there. You're not going to see it. And then there's a coupling between, which is again a bunch of inductive loops. And what you see up here is used to read out the state of the qubits. And as we were discussing at lunch, you do multiplex reading, so you read all of these qubits simultaneously. So you can know what the state of all the qubits in single shot. And you can prepare it again and again, maybe 100,000 times in a few seconds or so, maybe maybe our rep rate is close to 10 kilohertz at the moment. So you can repeat your circuit and your algorithms with a rate of 10 kilohertz. So you get a bit string with that rate. If you are not into computer science or the gate language and whatnot, you can think about this as a real physicist. You have a Bose-Hubbard Hamiltonian, meaning that if you excite these qubits, the photon excitation would hop around, and that would be the governing equation for these microwave photons going around. And these are the range of the parameters that is achievable for us. You good? Okay. So the first task is coming from both technical and hardware-oriented and computer science-oriented. With all this investment into quantum computing and into this industry, you can ask, is there anything, you name it, that you can define a problem, that you can outperform a classical computer? This came from John Preskill in 2012 or so. It was the most natural question to ask. And, working with the hardware, these things are falling apart every minute, and you really have very little chance. So with the freedom of defining the problem you like, can you do a task that outperforms a classical computer? So all this investment has at least some level of justification. You're responsible using the taxpayers' money. Here's how we define the problem. And if you know more, or I can confess at the end, that how we defined it to be very advantageous for our hardware, so we can beat the classical computer. We took a couple of very smart choices, so we could have a chance of winning a classical computer. You have a 2D grid of qubits. You are watching 1 by 9. Here is 6 by 9, and one of them didn't cooperate. So you have 53 qubits there, and they are coupled in a 2D grid. And someone hands you a sequence of gates, single qubit rotation, 2 qubit rotation, and says, what is the outcome? What is the output? What is the wave function coming out? You are going to sample from the bit strings, from the distribution of the bit strings, which are associated with the, according to Born rule, to the probability amplitude of the wave function. And you're just going to sample this. As I said, you can do 10 kilohertz, so you get a bit string at 10,000 bit strings every second. And we are going to claim that we know they are coming from this evolution. There is a unitary evolution, and we are predicting it. So there's theorems which says that this is a sharp p-hard. I don't know what sharp p means. Probably you know better than me. Wikipedia knows better than all of us, so you can look it up. It's sharp p-hard problem, whatever that meant. But technically, I can explain why it's a hard problem and how we are going to benchmark. There are 2 pillars in this business. One is that you have to create something complicated. But everyone who made a mess in the lab knows creating something complicated is not difficult. You just open a water fountain and something complicated comes out. But you have to be control over that. You have to predict that. You have to know that it does exactly what you like it to do. It's not just make a complicated thing, you just make a mess. It's just be on top of it. Well, another pillar of it is so there's complexity, which is rather easy to achieve, and this is technically in the lab is rather easy to achieve. Proving theoretically could be a hard thing. Our scheme was to create something complicated. Was that if it uniformly explores the available hyperspace, then it should be R, meaning that there is no symmetry in the problem. If it's not uniformly available in available space, this is a schematic how you follow something you might be familiar for a ball moving in a billiard ball moving in a billiard table. If it's avoiding certain region, it means that, okay, you don't need the entire region to simulate it. Probably there are more symmetries in the problem, so it can be simplified. But if you break all the symmetries, which is the case for a random quantum circuit, then probably it's hard. So that's the notion of complexity. And now I'm about to tell you about how we did the fidelity of it. So to get the fidelity, the simplest thing to do is to compare the bit string you get with the bit strings that you meant to get, or the probability of a given bit string. P is the probability of bit string I, and QI is the numerical simulation probability for bit string I. So this notion of entropy tells you that are you getting the bit strings that you have to get. In the actual life, the relation is a bit more complicated because you have to normalize it, you have to be sure asymptotically you get to 0 when you have lots of mistakes and whatnot. And that's the formulation for entropy, fidelity called cross entropy benchmark. In the actual experiment, it got a bit simpler because the bit string would not repeat itself. You have 10 million bit strings, and the Hilbert space is 10 million billion dimensional. So it's a bit more into it, but nothing important. So this is the vertical axis of the fidelity. And we're going to see how our fidelity is scaled with the number of qubits. So, but one thing I didn't tell you, and it might be philosophically perplexing, is that how are we going to prove that we could not do it? How are we going to be sure that we just didn't throw our hands up in the air and say, oh, well, we don't know how to do this, so it must be difficult. You have to prove without doing it. If you could do it, then it's not hard. If you see the chicken and egg problem? Okay. So it happened that the composition and this is very sensitive on gate choices. If you do a sequence of gates, which is EFGH, EFGH, that's simple. I explain to you in a second. If you do a different pattern, ABCD, and then the second time you don't exactly repeat it, you do CDAD, and then after it's 8th time you start repeating it, it's different, right? You see that? This repeats itself after every 4 times, this repeats itself after every 8 times, okay? These are very different in terms of computational complexity because some genius told us that this can be simplified. So what I'm saying is the following. So you do your single qubit operations, you come to 2 qubit operations, and every qubit can be involved in either left, right, or front or back. It cannot be involved with more than 2 qubits at a given time. So you have choices. So this choice of pattern and repeating it is rather simple. So what happens is that the fidelity of the gates, unless you're really something very strange happens in nature, the fidelity of the gates, the fidelity of the operation would not be sensitive on which one I do. You know, if a gate is bad, it doesn't matter it happened on cycle 6 or on cycle 8. It could matter, but in the limit that we are in the we're given the depolarizing noise model being a good description and there's enough randomness in the circuit, is really not sensitive to those details. If a bad gate is bad, if it repeats 5 times, just 5 times, doesn't matter when it is done, okay? So we can use the lower pattern to simulate, to figure out what's happening and make a claim about the top pattern without being able to simulate. Of course, the first thing we do, we don't even go full circuit. We just divide it into 2 sequence of 25, 27, 26 qubits. So that's simplifiable. That's not a big system. There's no gate connecting the left and right. So that's a simple case. And then we can measure the fidelity. Everything is fit in your computer, rather, more or less, depends how big is your computer. And you can get the fidelities going down, but you can also do it for both patterns, okay? Life is good. Then you can do something called alignment, which means that in the very first few cycles, you don't put the stitching connection of gates between left and right. It's only later on, you know, gates 10, cycle 10 onward or something, you start connecting the left and right. So this gives you enough slack room that you can simulate it again. You can have 2 systems and then you connect them later on. I get into in a second how you simulate this thing. And that's enough to be simulatable in both ways. So you get these green points in for the alignment. But when you do the full circuit simulation, of course, in this case, you can simulate it and say, you know, how well I'm doing. You can measure fidelity. Here, you cannot do it. That is our claim to supremacy. That, you know, the time it would take to do this, given how things are scaling up, and is very, very long, and it's just too long for us even to run. Okay, but you might notice there's a little cheating in here. There's a well, there's several keys. One of them is that we are putting a very stringent constraint on the classical computer. We say simulate and give me the wave function. On the hardware side, I have error in the order of 999, meaning that every bit string most likely is wrong. Well, there is probability, right? If there is no right and wrong. But the fidelity is close to 0.1%, meaning most of the thing you're getting is garbage, but still better than what classical computer can do. So this is unfair, which we ask the classical computer to do full simulation, and we do only do have certain notion of fidelity. Luckily, this is not hard to be taken care of by the classical computer. You can relax that on a classical computer. You say, hey, classical computer, you can also make errors as much as we make errors in predicting the bit strings outcome. And then life gets simplified. You know, there's a factor in here between the red and the gray numbers, which is exactly that factor of fidelity. And yet, nevertheless, this infamous number of 10,000 years come from the fact that we allow this to be a fair comparison. Okay, so this is our claim to supremacy, meaning that if you believe the sequence of the gates didn't matter, and if you really want to do the full circuit, the time it's needed is about 10 million. That's what we claim, and we celebrate it. Okay. Okay, let me tell you this, and then we get to the latest. So how did this quantum classical simulation of this work? If you tell me how long it takes to do it, this is the number of qubits. This is the simulation, if you can want to do this in your laptop. And this is the depth, how deep you go. And notice, and the color is how long it takes. So if you have 30 qubits and you go to depth 15, in a laptop which has 2 cores, it would take about a minute. So it's not that bad. So it's not really about depth, it's about number of qubits. And in fact, if you have 40, 50 qubits on a supercomputer, it would take an hour. Okay, in a whatever supercomputer which has about 1 million cores, I don't know, that probably exists somewhere. It has about, but here, but this is the lower axis. Now, please pay attention to this top axis. This computation, this is important. Take my word on it. Has to be done in RAM. Cannot be done on the hard drive. It has to be done on RAM. And on the planet that we live in, this is the size of the RAM available on a supercomputer. I don't know New York belongs to which planet, but apparently they can just go beyond that and claim that the computation takes a day, of course, but there's no supercomputer for us, at least, that we know on this planet that has that much memory. So it's not an argument about how long it takes. We understand it takes about a day. It's just there's no place to fit that wave function. Okay, life is not that simple. You can trade off a space and time, and you can say that I was showing you this batch, patch, and elide. So you can say I have a smaller system and consider the time, the way they connect to each other in time. That goes exponentially hard in time. Now look at the different patterns where things get read. So you have 30 qubits. Now it gets okay. Pay attention to the minute time. That's nonsense. We try to save. You're saving money for that. Stupid motivation. But you see, it's different patterns. So you can do trade-offs. But the claim was that there's no trade-off you can do to outperform what you have claimed. That was the claim. And we're happily living till something came up. So many people try to take joy of proving us wrong. That's a very good incentives, I guess. And they did lots of numerical work to show that this can be simplified further. And we are very happy that we have inspired this line of research, which is all based on figuring out how to do tensor network contractions. If you look at it for a long time, you figure out there are other ways to do these tensor network contractions, which allows you to do the same computation we do in a shorter time. So I have news. What we claimed that it took 10,000 years, it now takes this much. So we are not the record holder anymore till we outperform it again. But someone wise wrote this in our article ourselves. We predicted this, okay? So I covered our rear end. We expect to lower simulation would be achieved. But the point of the matter is that the one who is exponentially scaling, another one is just totally different way of doing the physics. Right? Technically, it's not very hard for us to add a couple of qubits, but it's very hard to make two buildings full of supercomputers. So we said that, and I think this race is going to go, and stay tuned. Maybe we can outperform them again, and we'll come. So, but that's the story of this. So let's see. Let's see. I tell you what happened next. So we're saying, okay, we define the problem ourselves. We outperform a classical computer. That's great. But what about interesting physics problem? This nagging voice of people, right? It's like, what about solving something physics problem? What you can do? Okay, so that's the next level of questions to ask here. So we did some investigation of what kind of problems can be solved without having an error-corrected quantum computer. So there is this region that you make thousands of qubits and you do error correction. They don't need to be perfect qubits. They just have to have 10 to the minus 3 or so in terms of fidelity errors. And you make it fault tolerant. That's perfectly valid, but that's not the subject of the rest of the talk. The rest of this talk is about you have a few qubits, a few tens of qubits, and you what kind of physics problem can you solve? If time permits, I talk to 2 examples, if not 1. And this is what we think is going to come to our horizon as we are approaching, as we are trying hard to do this. So, yeah, well, so there are several manuscripts and whatnot. I chose 2 of them that I explained to you how discovery in this NISQ. Did I define NISQ somewhere? Okay, noisy intermediate scale quantum. That's the phrase. How the discovery looks like in here. And you see a sharp contrast between that outperform a classical computer with this one. Okay, the first example I chose for you is done in collaboration with Stanford and Princeton and Max Planck, and it's about time crystal. The popular articles written on time crystal is full of facts and misunderstandings. You can read this one that we wrote in physics work that would be a little better maybe in terms of explaining the physics. And there's of course the original art. So what is the story of time crystals? And yeah, what is this crystal? When you look around yourself, you see lots of crystals. You're familiar with the concept of crystal, meaning that many atoms, many degrees of freedom organize themselves in a periodic pattern in space. You do not have any hard time finding the spatial ordering from liquid crystals to minerals and or ferromagnets, antiferromagnets. They all ordered in space, a pattern that repeats itself over and over in space. But you might say, you know, thanks to Einstein, maybe time is a space and space is time. So maybe we should find same order in time. A pattern that repeats itself in time. And you know, it's not hard to come up with examples. A clock, a solar system, you know, well, 2 planets in the solar system. The temporal ordering can be found, but there is a sharp contrast between the 2 examples we find. The lower ones, the time ordered ones, the ones that have a pattern repeating time, has far less degree of freedom. They are really 2-body physics. They are not many-body physics. So, so you can really challenge by posing a question saying that can we find a system which indefinitely oscillates in isolation without intake of energy, without dissipating of energy? Can it indefinitely oscillate? Okay, so there are 4 components into this definition: isolated, indefinitely, many-body, I guess 3 or 4. Yeah, well, it can also be a phase of matter, not a fine-tuned case that you know you cannot repeat yourself. So what we are saying is that this. If you have a lattice and you plug it and you disturb it, this perturbation decays very rapidly and you get back to where you start. If you manage to have a bunch of interacting pendulum which are oscillating in some nice pattern and the pattern repeats itself in time, if it gets disturbed, it would not come back unless the energy is dissipated somehow or energy is injected. This is very common observation, but this is not an impossible observation or challenge. So we are going to elevate it to the level of a definition or a quest, and we are going to go and try to find it. So that's the story of time crystal, to stay within this definition and see if there is anything satisfy that, because it's not against the laws of physics. That short definition I had could be expanded into a little lengthier definition, and hence figures of the paper. You need to have a sequence of gates, and for an extended range of parameters, you have to show the same physics, not a single point. You have to prove the closeness of the system. You cannot, it's not an open system physics, so you have to show it is stabilized against open quantum system effects, which are very dominant, in fact, in our system. So I have to make up some argument, and hopefully you believe me on that. We have to show that, well, the physics we are going to use is the physics of many-body localization. So we have to show that the entire spectrum is localized. And this is the way to show the eigenstates, eigenvalues of a Floquet operator. So it's just like a picture of a spectrum and energy eigenvalues. And the theorists have these very weird habits of asking you to go to infinite system size. They don't know how much resources you have, but they keep saying, go, what happens in the thermodynamic limit, infinite time, infinite system size. So we cannot do that. What we could do is to at least show some finite size analysis. Okay. So let me introduce you the pulse sequence we are using now. This is different than the supremacy case. Here's what we do. We start with transverse fields Ising Hamiltonian, but we do the kicked version of it, meaning that you don't realize the Hamiltonian, you realize a periodic Floquet version of it, meaning that you rotate the qubits, and then you do the Ising ZZ intercoupling, and then you put a disorder, and then you repeat this pattern over and over again. You choose your disorder values of phi1 to phi n and h1 to h20. There was 20 qubits in this case. And as soon as you choose them, you just want to repeat. So there's no Hamiltonian for this, or there's no unique Hamiltonian for this case, but the whole symmetry and the whole physics is rather insensitive to that. So it's a unitary dynamics that captures the same physics without having the Hamiltonian. Well, maybe so you guys can tell me, I have to finish at 4 or 4:10? At 4. Okay. So it's okay. So let me show you something boring, because I want to make a clear case that how this many-body localization is different. Sorry, this is different than child and string and whatnot, and what kind of physics of it was classically observed, and what aspects of it is very pure quantum physics. In the limit that there is no coupling between the qubits, let me suppress the entangling gates and whatnot. You're applying x to the power of g. When g is close to 1, means a qubit goes from north pole to south pole and goes back and forth. Okay, so as g equals to 1, a qubit goes up and down, and you do the z projection measurement. You see that it just goes from south pole to north pole over and over again, and this is the Fourier transform of this signal. Okay. So this is only applying this term, and I'm suppressing the other terms. Now, if G starts to deviate from 1, become smaller, you start from, let's say, North Pole, you go almost to South Pole, and then you don't come back completely, and you start to lagging behind, and you see this nice beating pattern. Okay, this is a single qubit operation. I'm showing you the expectation value of Z of one of the qubits, or the average behavior of the qubits. They are all doing the same boring thing. I can show average or single. And then you can make G to be further and further from 1. So this incompleteness become more and more visible. And you see the beating pattern and the Fourier domain. You can very easily see that there are, in fact, 2 peaks in the oscillation. Okay, nothing extraordinary. Something is slightly interesting happens when you turn on the coupling between them. Now you see the Fourier peak got locked at 1, in spite of the fact that G was still deviating from 1. Let me do one more time. So G starts deviating. You see 2 peaks in the Fourier domain. Now I'm going to turn on the interaction. When you do the interaction, it seems it brings some phase rigidity to the picture. And now, regardless of G being off or imperfect, you always get the periodicity 2 back. Okay? You only have single frequency. Everything gets locked in, and you have single frequency in spite of the fact that G is deviating from 1. So I can summarize this in this schematic. You start from a configuration, and this configuration goes to its opposite one, and then 1, 3, 5, 7 show you one pattern, 2, 4, 6, 8 show you the different pattern. So this is the phase locking that you are familiar if you have attended the concert and start clapping at the end of the concert. And you see people are synchronizing, or you know, fireflies in Thailand or Tennessee do the same thing. They don't know anything about quantum mechanics and do that. So up to now, there's nothing quantum about this phenomenon. It's just phase lock. Okay, so don't oversell it. And this has been observed by other teams and whatnot, that they make their G imperfect, and then they introduce interaction, and then they say, boom, everything gets back to single figures. So that is not the novelty of the physics. We can skip this one. Yeah, this is only one aspect of the physics. I think what I'm trying to say is that the time crystal physics has several components to show that you have a stable phase of matter. You have to really show all these components happen in your platform at the same time in your system, so you can claim that you have observed time crystal. Otherwise, each piece of it can be seen in a classical system in a different setting and whatnot. It's just coming together is what really mattered, and that was this manuscript was all about. The biggest challenge we had was to prove this isolated physics. Of course, the physics is not isolated. The system of qubits is not isolated. It's coupled to the environment. So the way you can purify, you can disentangle these two physics, separate these two physics, is by creating a fancy way of identity. Meaning you evolve the qubits forward and you evolve them backward. Technically, this should be identity. So if it's not identity evolution, meaning that there is this, whatever causes this is these open quantum effects. So this is the dynamic I have been showing you, the blue one or the red one when the parameter is in a different parameter regime. And the identity one, which you don't need to do any math for it, it has to be at 1. This expectation value has to be perfectly at 1. This is dropping, and this is exactly down to open quantum effect. So if I remove this effect from my blue signal, then I arrive at something which is purely down to internal dynamics. Because when you look at it a priori, you don't know if it's because of internal dynamics thermalizing, or it's internal or open quantum effects, which is leading to. So to remove them, of course, the simplest thing that a grad student would do is just to divide these two by each other. And after pages of fancy mathematics, it turned out that actually that's the answer. So the simplest thing that came to my mind was actually the correct answer. That's beautiful. you can't beat that criteria. Okay, so here I'm showing you two curves. The blue divided by black is in here, and the red divided by black is here. So we have two distinct phases, G 0.97. It seems in totally different phase place than G equals to 0.6, but that's, I would not talk too much on it today. But you can see that now this is our claim of removing the open quantum system effect. And this is where we start claiming that this oscillates indefinitely. Okay, this is indefinite for experimental physicists. If you want to wait 10,000 cycles, I can't. So also I show you the spatial pattern, meaning that this is not a cherry-picked qubits which does this. This is boring, and it's good that it's boring. That every qubit is up, and then every qubit is down, and then, well, it's ZZ. So if it was, there's a, yeah, multiplied by its initial state. So it's initial configuration, opposite, back, up, parallel, anti-parallel, and so forth. So yes. Oh, question now. So all 20 qubits are doing the same boring thing. And so we are saying that this is our evidence for time crystalline behavior. This finite size scaling I promised I would show to you is done by not making the chain longer, but making the chain shorter. You can do that too. So you have 20 qubits, you start cutting off qubits from the ends, and you look at a control parameter, which is in our case is G values, and then the order parameter in this case come from the spin glass literature, which is 2-point correlation function, sum over all possible combinations of qubits. 2-point correlation function, very famous at the time, very much used at the time of glass physics. Has nothing to do with the glassy behavior in here, but it's just say add these correlations and see that are they building up or they are not. And you see a clear crossing point below which I zoomed in here. The order parameter. Oh, okay. When you go larger sizes, the order parameters start to diminish. Here, above the transition, when you go larger sizes, the order parameter goes further and further up. So that is our evidence for time crystalline behavior. I'm not talking about a couple of things more technical related to many-body localization aspects of it. But the point I'm trying to make is that this is a holistic picture, and just seeing an oscillation, just seeing many-body localization is not sufficient. Otherwise, yes, a single pendulum is as good as it needs to get. There is a definition. Okay, so I have 8 minutes left, right? And I have one more paper. So maybe we don't get into this, and I answer questions, or what do you like? Okay, so, okay. Stay tuned. I'm going to give a fast version of this physics. This is a different mode of discovery. This was done internally by my colleagues at Google. The physics we are interested in here is the physics of bound state formation. This is the famous Heisenberg model, which you have excitations or spins interact with nearby, and there's an interaction terms and there's a hopping term. And in this Hamiltonian model, which is solved 100 years ago, there is a prediction that there is a bound state can be formed. And I explained to you what bound state means and is. We are focusing on a Floquet version of the same Hamiltonian. The bound state for the Hamiltonian has been observed when it's about here. But here we are going to do the Floquet version of it. And I tell you the importance of it is in maybe a technical, well, it's a charming physics in the following sense. When you have an exciton in the semiconductor, there's a semiconductor gap, and in the middle of the band gap, you have an excitation. So the excitation has nowhere to decay in terms of energy. And that's where the stability of it comes from. That's this lifeline is coming from, essentially. However, imagine you have a scenario that you have a band of states, And this bound state could not care that is overlapped with the continuum of the states. You're energetically at the same place, but there is no decay from one to another, and that comes from the symmetries of the problem. So it's kind of a cute thing to focus on. And here is the Floquet version of it schematically. You have a band of states, but yet there is no decay from your bound state to those states, in spite of the fact that are energetically overlapped. So let me tell you what the bound state is. It's if you excite a couple of qubits next to each other, bound state means that this stays together for forever. For the most part of the wave function is in this configuration, meaning that every time I take a snapshot of the system, I find my zeros and ones. Let's call them ones. These ones would be next to each other. And that's a very amenable thing for our platform, and we can focus on it. We can do it rather easily. So here is our experiment. So I put the 24 qubits in a ring, and we are going to excite 2, 1, 2, 3, all the way to 5 qubits. And I'm going to come back and ask them different cycles, where are the excitations? And I do it, I don't know, 500,000 times, and I add the measurements. When one excitation, there's nothing to bound to, and this is just doing some happy random walk on this loop, and you see a very nice interference pattern, single photon, nothing complicated. And when you have 2 excitations, you see that there's or more, you see the concentration of color indicates that photons didn't want to leave each other. They want to be together. And if they move very slowly. Okay. Let me do a little analysis of this. So the bit strings I get, I'm going to factor it or group it in 2 groups. One group is the time that these excitations are next to each other. Okay. And another group is the group that they are separated and they're not next to each other. And if I just look at these the times that I found the answer in this group, and I just say, okay, they're together, so I represent this with a single point. I highlight the center of mass of these. I see a pattern which is very much similar to that pattern. It's just a slope. And the same goes for 3, 4, and 5. Meaning that these are happily walking together without getting away from each other. And the significance of it is the following. You look at these configurations, if you have a ring of 24 qubits and 4 excitations, and you consider the cases these are indistinguishable particles, and then you consider the cases that are next to each other, there are only 24 possibilities, right? If we choose which one is starting, which site it starts, then the other just follow. They're just next to each other. So there are 24 possibilities for this. However, the cases that they are not next to each other, in this particular example I said, there are about 8,000 possibilities. So they stay in the corner of the Hilbert space, which is made of 24 states, dimensional space, and then they avoid these 8,000 other places that they can go. And that is the power of symmetry into this example. Okay, we did a little spectroscopy of this. Some technique, Fourier transform technique, we can resolve these bands and we can see that this is the, for those of you in the condensed matter business, probably you won't see this quasi-particle, what is this energy versus momentum. So we could do it up to these 5 photons that we have done. And the band's getting flat, indicating it's getting massive, more massive, and then this overlap that I was mentioning become more evident for us. And we can do the charge of it by putting flux in it. But I want to tell you where the discovery comes from. Okay, our guru wants us to do something which is called breaking integrability. Integrability was the symmetries that gave us this physics. So you go to Igor Aliner, who predicted this, and say, what happens if I break integrability? What happens if I add more qubits in the ring, which breaks the integrability, and now that excitation have had go more places. Okay, the prediction is that as soon as you break this integrability, which is a strength is set by this theta prime, as soon as this theta prime become non-zero, the bound state is gone. So that's what we are going to do. We are going to, but from the spectroscopy case, this is the band of 3 photons, which is overlapped with the other bulk continuum now. We have seen this ourselves, measure it correctly, and we are going to see what happens if you break integrability. And the simple thinking is that you do Fermi-Golden rule, and then they break. Easy, rather quickly. And by now, with the tone of my voice, you realize that's not what happened. So, right? This is the measure of how intact they stay. This T-bit string, S-bit string, I said, is a measure of how good they stay together. And as a function of cycle, there is some decay out of dephasing in the system. But the prediction is that as soon as you put some theta prime, this is the strength of the perturbation, it would just boom, drop down to these yellow. However, you realize in the experiment that theta prime, when theta prime is as strong, the perturbation is pretty strong, as dynamic. This is really not is happening and is really close to each other. Let me show you more data so you can really change your perturbation gradually, and you can see that the bound states remain intact for a very good time. And this is the same cut into the same plot. You cut in here and here, you see that the bound states stay together, and then breaks down further down. It is not quickly coming down. And you can do that to the momentum space picture I mentioned. You can look at this. This is the width of the band of the bound states. And it goes down, of course. You hit the qubit with a hammer at the end of the day, it's going to go. But it's nothing to do with that naive usage of the Fermi-Golden rule. We're not going to question the Fermi-Golden rule for today, but we are just going to say that we don't know how to use it. And this was a discovery because we didn't anticipate this. This was not beyond what the classical computer can do. I bet you can start programming this. This is 24 qubits, 4 or 5 excitations. It's 8,000 dimensional Hilbert space. You can handle it in your laptop. But nevertheless, we are the first using our quantum processor to find something which was not found otherwise. But now, of course, numerical can certify that. And there are a couple of candidates for why it is. And I want to emphasize that the numerical simulation came only after. And that's how NISQ discoveries are supposed to look like. Yeah, so if you invite me more, you're going to hear more of the same things for the next few years. That's my conclusion slide. Thank you.
Thanks, Pedram, for a very nice talk. We have some time for questions.
So if the enough to have the for say, I guess how do you encode it?
Okay, there. Let's see, which is
In your first, when you're talking about
no fermionic. Well, maybe here is not a bad place. No, you okay. Let's talk about this gate, the 2-qubit gate. This 2-qubit gate. This is the unitary associated with it. Has two places that you can pay attention. One is this hopping. This theta sets the hopping. So if photon sitting at a side, it hops. That is now irrelevant of if it's next lattice side is unoccupied, it's just going to hop. This is how often it hops. And this is the XX plus YY in the Heisenberg Hamiltonian. This is the interaction terms, meaning that if 2 photons are in next qubits and rubbing shoulder, that's the phase they accumulate. Okay? And we can go for any values of theta and phi that we like, more or less. Okay, so this is this gate. Now, now coming here. So your question is, so the fermion physics is really about, I mean, we can do any fermion physics, but the bigger challenge is in mapping, is in the going from these excitations in this case are photons or bosonic excitation, no exclusion principle for them. And now you have to have, let's say, Jordan-Wigner transformations, one way of doing it. Now you can talk about the fermionics. And that mapping is non-local, and that's a major headache. That is the bigger challenge to realize chemistry problems. Otherwise, any range of dynamic of electron can be translated to these spin languages. It's just overhead of something which is localized in the fermionic land to something which is delocalized in the qubit spin language land. That's the thing. Am I answering? No.
So I guess my question was, is this like an appropriate mapping to use
Fermionic problems?
Yeah.
No, there is no mapping to. This is the study of transverse Ising model. There's no fermionic problem here. If you come with your fermionic problem to me, then we have to choose the mapping. Jordan-Wigner is one way of doing it, but all the mappings that I know of are non-local and are major headache. But here we do talk physics here, and the next example and all that. There's no reason to go back to the fermionic. There's no need to talk about fermionic picture. I'm missing. No.
We can chat after. I got misremembered exactly.
Yeah, give me a second. Ising model is this. Sigma z on each qubit, and then, sorry, sigma x on each qubit, and zz, this is the spin version. Well, the one you know, they're all in the same exponent. Here we do the kick version. They all come in a different parts. They are not commuting, so I cannot. E to the A, E to the B is not E to the A plus B because they're not commuting. I think the one you know is E to the A plus B. E to the A plus B, which is ZZ and X. Yes. Okay, so there are some delicacies in the, well, you have to, okay, the whole thing, which is in fact known as from John Lennon also, it's about realizing a many-body localized system. So you have to prove the parts that I didn't talk, that you have a many-body localized system. Any of these components that you take off, you would not have a many-body localized system. In particular, I try to emphasize in here that this order has to be in the landscape. That's, of course, the minimum thing, and also has to be in the coupling. If it's not in the coupling, there is no many-body localized physics. And the way to see it is this schematic is showing you. If these 5 values were uniform, you can forget about them in a second. You have a qubits, you flip them, and they see a disordered landscape. Beautiful. You flip them again, let's say G is close to 1, and they see a disorder, but the disorder in the eyes of the qubit looks totally inverted because now they're upside down, right? They're very angry the argument. So after 2 cycles, the disorder and it's exactly opposite would cancel each other out. And that's an intuitive explanation why you do not get many-body localization in here. So without C-phase gates and with this being not CZ, but being C-phase, meaning that phase is adjustable, you have no MDL, okay? And that's a key silence feature of the paper I didn't talk about.
And then by different technology, by the localization, we mean that the data and the blood are
By localization, we mean that we mean that if you put an excitation in the system, it doesn't go anywhere. You locally perturb and you go a few lattice sites down. Those qubits have no knowledge of information, does not propagate from one place to another. So you can give it a very simple spatial interpretation. You don't need to go to 3D. So,
I have a question actually. So what stops you from coding made by localization in 2D systems? You have a 2D chip and
community, the embarrassment in front of community. No, yeah, I would do it. Let's do it.
Okay.
Yeah, no, there's this folklore of vibe of, oh, there's no MDL in 2D. In fact, someone showed evidence to contrary this morning, so maybe I should take it seriously.
I guess you could just check it, right?
Well, the thing is, if you do it, they say, oh, you didn't go deep enough, you didn't go large enough, you didn't wait enough. Even these, they would say it would melt or goes away if you wait age of the universe. Like, well, I don't know, even Atlantic Ocean is stable with that level. Yeah, so no, there's nothing stopping us. I think we should treat it. It's just thing is hard to prove. If yeah, you can disprove a claim, but not proving it is a very bad asymmetry.
So you had this statement where no sort of requirements in the system which is considered. I don't know.
No, I didn't say that. For the supremacy, I said that when you're doing random gates, there is no symmetries that you can know of. So that was our claim, that the entire Hilbert space should be explored because there's no symmetry to funnel you to a certain part of the Hilbert space and avoiding the others. Here, I didn't make any claim about the symmetries. You see as much as I see here. This is what we're gonna do. What are the symmetries? I don't know. Yeah, you put the local disorder in Z and coupling, and that's what we got. I don't know. How big? What has to be? So I'm not sure if it's well, crudely speaking, very roughly speaking, I can add one qubit and you have to build another supercomputer that's the same size, right? But of course, there's delicacies in the argument on how we do things and whatnot. So it's just what I'm claiming is that the scaling is different. They have done experiments more than 50 qubits now, and yeah, still someone could find a way to partially fit it and whatnot. Because here you can trade space and time essentially. Let me go back to this. You see, there is a trade-off. You can solve this problem which is two pieces and they're connected only sometimes. Or you can do four pieces and then you consider all the way that these four pieces connect each other. So there's always this trade-off that we make it a very case-dependent study.
There are no other questions. I think we can stop here and thanks, Pedram, one more time.
Sure.